This video is an introduction to differential equations. A differential equation is an equation that consists of a function and its derivatives. The most common application of differential equations is creating mathematical models to approximate real situations. In differential equations, there are three types of variables. The first one is independent variable. This is the variable with respect to which derivatives are obtained. We also have the dependent variable, which is the variable that is being differentiated. Then we also have the parameters, which are the variables other than the independent and dependent variables. For example, let's say we are given the differential equation L times d squared I over dt squared. Of course, this is the notation for the second derivative of the dependent variable I with respect to the independent variable t. Okay, plus r times di over dt. Now this is the notation for the first derivative of the dependent variable y with respect to the independent variable t. Okay, plus 1 over c times I is equal to e times omega times cosine omega t. In this differential equation, the only independent variable is t. That's because the derivatives are all with respect to t. And the only dependent variable is I because the variable that is being differentiated is only I. So d squared I and di. How about the parameters? Well, we have all the other variables. So we have L, R, C, E, and omega. By the way, this should be omega instead of W. Next, let's say we have this differential equation, d squared v over dx squared. This is the notation for the second derivative of the dependent variable v with respect to the independent variable x plus d squared v over dy squared. Now, this is the notation for the second derivative of the dependent variable v with respect to the independent variable y. So that is equal to 0. In this differential equation, we have, okay, for the independent variable, we have x and y. Because this derivative is taken with respect to x, while this derivative is taken with respect to y. So for the independent variables, again, we have x and y. For the dependent variable, we only have v because we are differentiating only v in both expressions. Okay, how about parameters? Do we have any? No, we don't. Okay, therefore for the parameters we have none. Now let's consider some examples of differential equations. Okay, so first we have a dy over dx. Again, this is the notation for the first derivative of y with respect to x, that is equal to cosine x. Okay, next we have d squared y over dx squared. Okay, so this is the notation for the second derivative of y with respect to x. Okay, plus k squared y, that is equal to 0. Next we have y double prime. Okay, y double prime is another notation for the second derivative. So, y double prime here in this term is the same as the notation d squared y over dx squared. Okay, so plus 7 times y prime. Y prime is another notation for the first derivative. So y prime is the same as dy over dx. Okay, so now we have to raise that first derivative to the exponent 3 minus 8y is equal to 0. Next, we have d squared y over dt squared. So this is the second derivative of y with respect to t plus d squared x over dt squared. So this is the second derivative of x with respect to t, that is equal to x. Next, we have x squared plus y squared, okay, quantity times dx. So this is the derivative of x minus 2xy dy, derivative of y is equal to 0. Now we also have d squared omega over dx squared. So this is the second derivative of omega with respect to x. And we have to raise that derivative to the exponent 3 minus xy times d omega over dx, which is the notation for the first derivative of omega with respect to x plus omega, that is equal to 0. Now let's consider the types of differential equation. There are at least two. The first one is ordinary differential equation, in which we differentiate the dependent variable with respect to all independent variables. For example, we are given d squared y over dx squared plus k squared y is equal to 0. From this equation, we can say that the dependent variable y is a function of x. Okay, so since in this equation we have to get the derivative of y with respect to all the independent variables. Well, in this case, there is only x. Okay, we can say that this equation is an ordinary differential equation. The second type of differential equation is partial differential equation, in which we differentiate the dependent variable with respect to only the indicated independent variable. In other words, in any instance of differentiation or derivative, we have to consider the other variable or variables as constant. By the way, the notation for ordinary derivative uses d. So we have d squared y over dx squared. For partial derivative, the notation uses the lowercase delta. So we have here delta u over delta t. Okay, so let's say we're given this equation, delta u over delta t is equal to h squared times quantity d delta squared u over delta x squared plus delta squared u over delta y squared. Based on this equation, we can say that the dependent variable u is a function of t, x, y. Okay, so again, u is a function of three independent variables. We have t, x, y. Okay, so this expression delta u over delta t signifies the first derivative, of course, but since we have here delta instead of d, okay, this is the partial derivative of u with respect only to t. Okay, so in other words, if we differentiate u, we have to differentiate only the factor that involves t, because we have to consider x and y as constants. Okay, how about this one? This is a second derivative, partial, because we are using delta, and this is the second derivative of u with respect to x only. So if to differentiate u, we have to differentiate only the factor that involves x, and we have to consider t and y as constants. Now in this term, we have the second partial derivative of u with respect to y only. So to get this derivative, we have to differentiate only the factor that involves y, because we have to consider t and x as constants. Now we have to learn the definitions of the following terms. First, we have order of differential equation, which is represented by small n. Okay, this is the order of the highest ordered derivative. For example, we have here y double prime plus 7 times y prime raised to the exponent 3 minus 8y is equal to 0. Okay, so to determine the order of this differential equation, we have to consider the we have to look for the highest ordered derivative. Okay, so yes, in this equation, there are only two derivatives, the second derivative and the first derivative. Of course, between these two, the higher order derivative is the second derivative. Okay, so the order n of this equation is 2. Okay, and we can say that this differential equation is a second order differential equation. Next, we have the solution of differential equation. It is a function whose n derivatives exist and which satisfies the equation. So why does the function have to have and derivatives, because in the differential equation you have to differentiate the function or the solution n times. For example, in this case, two times. So you have the first derivative, and second we have the second derivative. Okay. Yes, of course, the solution of a differential equation should satisfy the differential equation. Okay. um Now, what is the general first order differential equation? So first order. So we have to have only the first derivative. Okay, so dy over dx, that is equal to a function in terms of x and y. Okay, now this equation can also be written as, or can also be written in this form. Okay, so instead we have m, which is a function of x and y, times dx, plus n, which is also a function of x and y, times dy, is equal to 0. Now, what is a linear differential equation? Or how can we say that a differential equation is linear? In a linear differential equation, the dependent variable, usually y, and its derivatives are raised only to the exponent 1. This is the general form of a linear differential expression. Okay, so we have here b sub 0 or b naught of x, that is some expression in terms of x, times d to the n y over dx to the n. Okay, of course, n here is the highest order of derivative. So this is the highest order derivative in the equation, plus some expression in terms of x, times d to the n minus 1 y over dx to the n minus 1. So the order of derivative decreases incrementally by 1 until we reach this expression. So we have some expression in terms of x times dy over dx. So so in here we have the first derivative. So dy over dx plus some expression times the dependent variable y. Okay, so again, in a linear differential equation or expression, okay, the dependent variable y and all its derivatives, so dy over dx, and these two derivatives should be raised only to the exponent 1. Okay, let's consider some examples. Okay, we have here d squared y over dx squared plus 2b times quantity dy over dx raised to the exponent 3 plus y is equal to 0. So let's inspect the dependent variable y and the derivatives. So we have a d squared y over dx squared, second derivative of y. Okay, well, this is raised to 1. Okay, how about in this term, we have here dy over dx, the first derivative of y. Okay, but this is raised to the exponent 3. Okay, therefore, this equation is not a linear differential equation, or it is a nonlinear differential equation. How about this equation? So we have x squared y double prime plus xy prime plus the quantity x squared minus n squared times y is equal to 4x cubed. So let's inspect the exponents of y and its derivatives. Okay, we have here y double prime, that is raised to the exponent 1. We have here y prime, that is also raised to the exponent 1. And in here we have y raised to exponent 1. Now on the right side, okay, the expression does not involve y or any of its derivatives, Therefore, we need not inspect, okay, for the exponent in this expression. Now, since y and its derivatives are all raised to the exponent 1, this equation is a linear differential equation. Now, let's tackle the concept of families of solutions. Given a differential equation, we can obtain groups of solutions using antiderivative or integration. In other words, a differential equation usually has multiple solutions. Now, these solutions differ by arbitrary constant or constants that are represented by the letter C. Now, to be able to solve for the value of a constant, we should be given an initial value. When we say initial value, this is the value of the dependent variable or its derivative when the value of the independent variable is equal to 0. For example, we are given this first order differential equation. So we have dy over dx is equal to f of x. Okay, since we have only the first derivative, we can solve for the solution of this differential equation by integrating this differential equation once. Okay, so to do that, recall that f of x here is actually f of x over 1. So we can cross multiply dy times 1, that is dy, and dx times f of x is f of x times dx. Now, to solve for the solution y, we have to be able to eliminate this derivative on the left side. Okay, for that, we have to integrate both sides of the equation. So the integral of dy, so on the left side, the integral and the derivative will cancel out. Okay, so we are left with y. Okay, and on the right side, we can copy this expression. So we have the integral of f of x dx. Okay, and once you integrate, or since you have to integrate this expression, you have to add a constant c. Okay, again, after integrating an expression, we have to add a constant c. Since we have only one constant, okay, for the solution to a first order differential equation, okay, we need only one initial value. For example, let's say you are given the value of y, the value of y that is equal to a when x is equal to 0. Now, let's say we are given the second order differential equation. D squared y over dx squared is equal to f of x comma y. So we have here the second derivative of y with respect to x, that is equal to some function f in terms of x and y. Without showing the derivation or integration, we have the solution y is equal to the integral of f of x dx plus c1x plus c2. Now, since we have here the second derivative, okay, we have to integrate this differential equation twice in order to get this solution. Okay, so C1 here is due to the first integration. So after we do the first integration, we add the constant C1. So in the second integration, we also have to integrate C1. So what is the integral of a constant? It is the constant times the independent variable x. Now, C2 is due to the second integration. So after doing the second integration, we have to add another constant, C2. Since we have two constants in the solution, we should be given at least two initial values. Now, those initial values are usually the value of the first derivative of y. Okay, let's say that is equal to b when x is equal to 0. And the value of y, let's say that is equal to a when x is equal to 0. Now, to visualize the families of solutions or the multiple solutions, okay, to a differential equation, we can use the geometric interpretation. Let's say we are given the first order differential equation dy over dx is equal to 8 times sine 4x. Okay, so we only have here the first derivative. So we have to integrate this differential equation only once to get this solution. Okay, so the solution is y is equal to -2 times cosine 4x plus c. Now, this c can have any value. Let's say 1 plus 1 plus 2 plus 3 or any value. Therefore, this expression can generate multiple solutions. Now, this is the plot of the multiple solutions to the first order differential equation given in the previous slide. So, in this plot, each curve represents a solution. Okay, based on this plot, we have the following uniqueness property of families of solutions for a first order differential equation. Through each point in the plane, there passes one and only one member of the families of solutions. In other words, the multiple solutions or the many solutions to a first order differential equation do not overlap. Now, let's say we are given the second order differential equation. D squared y over dx squared is equal to 12x squared. Okay, since we have here the second derivative, we have to integrate this differential equation twice in order to get the solution y is equal to x to the 4 plus c1x plus c2. So again, take note that for a second order differential equation, the solution involves two constants, c1 and c2. If we plot this, or the plot of the, before that, yes, c1 and c2 can have any value, So let's say this is 1, this is 2, this is 0, or it is -1. Therefore, this solution, or this expression, okay, also generates multiple solutions. And the plot of those solutions is this one. Okay, so there are multiple solutions, but only three of the solutions are shown here. For example, this curve is the curve for c1 is equal to 0 and c2 is equal to 1. Now, this curve is the curve for c1 is equal to 2, is that 2? And c2 is equal to 1. There. Okay, now this curve, according to this part, okay, is for the case when c1 is equal to 0 and c2 is also equal to 0. Okay, based on this plot, we have this uniqueness property of the families of solutions for a second order differential equation. Through each point in the plane, there passes one and only one member of the families of solutions that has a given slope. So yes, according to this plot, the solutions of a second order differential equation can overlap at some point. For example, at this point and another point, another overlap at this point. But at each point of intersection, the intersecting curves have different slopes. For example, this curve has almost zero slope, while this curve has, at this point, has a positive slope. At this point of intersection, this curve has almost negative, some negative slope, while this curve has positive slope. If you have any question, please leave a message, or rather a comment.